Hi there, welcome back. We're on lesson 2 today, tangent lines and the derivatives, but I watched yesterday's video and realized if you'll go back to your notes on example 7, part B, I realized that I made an arithmetic mistake. I missed a 4 here when I simplified my work. So I want to go back and correct that. I did have the 4 minus 1 was 3, and this minus 3 was good to add up to 0. But on my next line down on my work yesterday, I said I didn't see the 4h, and I wrote down minus 2h. So that should be corrected with 4h minus 2h is a positive 2h minus h squared. And that's where I made my mistake. I had a negative 2h minus h squared. So factoring out the h, my correct answer should have been h on the outside, and then 2 minus h on the inside, divided by h, and the average rate of change would have been 2 minus h. That would have also affected part C, because on part C, we were asked to find the limit as h approached 0 of that expression, 2 minus h. And the slope would have been positive 2, not negative 2. So be sure to correct your notes from yesterday, or maybe you caught it while I was doing it and you figured it out on your own. The slope would have been positive 2 as h approached 0. So now we can move into the next lesson. And today we're going to talk about the two big concepts or big ideas in calculus. That's the tangent line problem and the area problem. Those are our two main ideas or two sections of calculus. In first semester, we look at derivatives. And second semester, we discuss the area problem and talk about integrals. And actually, both of these are related to limits. So last time we discussed and developed a slope formula using the difference quotient. And we said that that general slope formula would be called the derivative. And that formula is a function itself. And we're going to write the notation f prime and read that f prime of x. And we're going to see today that if a function has a derivative at a point, we say that that function is differentiable at that point. So like we said yesterday, we're going to define the derivative to be the limit of the difference quotient, and the derivative is the slope of the tangent line, provided that the limit exists. And we should make a note of the fact that if the domain of the derivative f prime consists of all the x's in the domain of the function where the limit exists, it could be smaller than the domain of the original function. And we'll see that as time goes on with some of our examples. We'll consider and come back and discuss this a little more. On this slide, you see the different notations and how to read them. So I'm giving you this for just a reference to go back. F prime of x, y prime, dy dx, which means the derivative of y with respect to x, and so on and so forth. All of these are perfectly legitimate methods for writing derivative in our course. So, you know, we've discussed the rule of 4, and graphically, the derivative at a point is the slope of the tangent line. Numerically, the derivative at a point is the limit of the slopes of the secant lines, and we saw that last time where we moved that secant line closer and closer. H approached 0 so that it was so infinitely small we could find the limit of the difference quotient. And verbally, we can say that a function is said to be differentiable at a point if and only if it has a defined slope at that point. And if a function doesn't have a tangent at a specific point, then the function can't have a slope there. I'm thinking about at a really sharp corner or vertical tangent line, which again, we'll see those kind of things as this chapter goes on. So let's use the limit process to find the derivative, the general formula for the derivative of this function 2x squared. And hopefully this time I won't make any arithmetic mistakes like I did on example 7. So same formula. We're looking at the limit as h approaches 0 of f of x plus h minus f of x divided by h, which means we've got to substitute x plus h here for our variable x and here for our variable x again. So x plus h. And in red, this is the f of x plus h portion. And then we want to subtract the f of x, which is just the original function, 2x squared minus 3x. So we're going to subtract the entire function, 2x squared minus 3x, and then divide the entire thing by h. So we want h to go to 0 when we take the limit at the very end. Expanding all of this, multiplying by 2 as I expand that binomial would be 2x squared plus 4xh plus 2h squared, distributing the 3, then distributing the minus, dividing by h. And like we said last time, if there's not an h in the term, it should be able to be eliminated. So the 3x and the 2x squared. And hopefully everything has an h left, so not missing anything. I've got 4x and 2h squared, so we factored out an h, leaves a 2h, and then minus 3 divided by h. Now we can take the limit. So I'm looking at the final expression here, 4x plus 2h minus 3. So applying the limit definition by substituting 0 right here, we're going to get the derivative of y with respect to x as h goes to 0 is 4x minus 3. No mistakes in that one. Here's one for you to try. So given y is x squared minus x, use the definition of the derivative to find f prime of x. So this time just using f prime notation. You might want to turn off the video, try this on your own, and then come back to check that you did the same thing as I did. So using that limit definition with the difference quotient, we have x squared minus x, and then minus the function, all divided by h. And you can see this is the piece from here to here. This is the piece that's the f of x plus h. And then this is the piece that's just f of x. So you can see the difference quotient there. Remember to keep writing the limit rule until you take the limit. Keep writing that expression. And then we're expanding the binomial, distributing subtraction, dividing by h, eliminating the terms that'll subtract out, factoring out the h from the numerator. This is a tricky one right here. Oftentimes that gets dropped. And then once you get to the end, At this place, you can look at that last expression and apply the limit definition by substituting 0. So the general form of the derivative is 2x minus 1. Now, do you remember what we said yesterday? That this is the general form of the slope of the tangent line for any value of x on our function x squared minus x. This is our function. This is the slope of the tangent line for any number you want to place in here. Okay? And if you think about the domain, this is a polynomial. The domain is all reals. And if you think about the domain here, this domain is also all reals. So we haven't had to limit the domain yet. In this next example, we're going to look at different forms, different ways of finding the derivative. And sometimes the AP exam can trick us with these definitions. So you have to be familiar with them. If you have a derivative at a point, you can actually find the y value and use the limit definition this way or this way. Let's see what our pull tab says. A function is differentiable at a given value of x if you can take the derivative of the function at that x value. In other words, f of x is differentiable at a point if the derivative exists. A function that's differentiable at every point of its domain has a derivative. This will be important when we get to justifying free response questions. So first we're just going to practice. Let's say we have the square root of 3x plus 1, and we want to find the derivative at our a value using one of those alternate definitions. So let's say, first of all, we're going to find what the f of 1 value or the y value is at 1, which is going to be the square root of 4. So the function value at 1 is 2. And if I apply that rule, f prime of a is the limit as x approaches a for f of x, which is the square root of 3x plus 1, minus the f of a, which we just found out to be 2, divided by x minus a. Let's go look at that. I'm using this rule. F of x minus the f of 1 divided by x minus 1 as x approaches 1. Okay? I just didn't write the rule down. Now, in this case, we saw before that we could rationalize the numerator. So if I multiplied the top and the bottom by the quantity radical 3x plus 1 plus 2, then we could eliminate that radical and simplify our expression. So the derivative at a, or at 1, is the limit as x approaches 1. I actually think I want to put 1 here. Okay, and then if we multiply by distributing this term to this term, I'm going to end up with 3x plus 1. Outside and inside are 0, and then the last terms give me negative 4. And I'm not going to touch the bottom. I've got x minus 1 times the radical 3x plus 1 plus 2 in that quantity. And what does that do for us? Here I've got 3x minus 3. Okay, so if we have 3x minus 3, we could factor out the 3 and end up with the quantity x minus 1, which conveniently is going to help us eliminate that factor on the bottom. And then we can substitute Uh-oh, need a little more real estate here to write. Then we can substitute into the end. So without writing again, I'm going to go ahead and substitute 1 into my x value here. So the numerator, the derivative at 1 on the square root would be square root of 3 times 1 plus 1 plus 2. So I'm substituting x equals 1 in this step to give me this step. And when you simplify that all down, the derivative at 1, I keep dropping my 1, trying to think and write and talk at the same time, we end up with 3/4. So the slope of the tangent line at the ordered pair 1, 2 is 3/4. Okay, observations for using the derivative formulas. When we're finding the derivative at a point, there's 2 different approaches. You can either find the general formula first and substitute your x value, or you can substitute the x value from the very beginning. So we've kind of done both things. And here on this chart, there's the 2 different ways. If you're given a point and you're finding the instantaneous rate of change, we're going to do this. And if you're given 2 points and you're finding the average rate of change, we're going to do the slope of the secant line. So this side is slope of the tangent line, this side is slope of the secant line. And you just want to be paying attention to what they give you before you just start to work. So here, example 4, they're asking us to find the slope of the tangent line of this hyperbola 2 over x at the point x equals 3. Okay? And we're going to use this formula because they've asked us to. So our a value, when x is 3, that's telling us this is our a value. And we want to go back and substitute. The slope of the tangent line will be the limit as x approaches 3. The function is 2 over x minus 2 over 3 divided by x minus 3. So what did we do? We substituted our 3 value in here to get the f of 3. So we need a common denominator, and we could do that by multiplying top and bottom by 3x, clear that fraction. So as x approaches 3, that's going to give us 6 minus 2x divided by 3x times the quantity x minus 3, which is convenient because now I can factor out from the top a -2 and end up with x minus 3, which will eliminate that factor in the denominator. And by doing so, then we can substitute into that final expression as x approaches 3 for the expression -2 divided by 3x, substituting 3 down here, then our slope is -2/9. On letter B, you might turn off the video and try to do the same thing with this formula. Then come back and check with me to see that you have mastered the concept. So in this case, the function was 2 divided by x, and I want to put 3 plus h, because when y is 2 over x and x is 3, we're using this format. And as h goes to 0, I'm going to pull out the 1 over h. and get a common denominator. 3 times 2 is 6, and 2 times 3 is negative 6, and negative 2 times h is negative 2h, divided by 3 times 3 plus h. So pulled this out front here and basically got the common denominator, 3 times 3 plus h. Okay. And what does that do for us? Well, let's see. We've got 6 minus 6, that's gone. And this h up here can take this h out here. And we're left with the limit as h approaches 0 of what, negative 2 on the top and 3 times 3 plus h in our denominator. And now I can substitute h as 0 and find the limit. So as h approaches 0, our slope is approaching negative 2 over 9. So whichever method you prefer, whether it's this formula here or the one we did on part A, as long as you follow the rules, you won't have any problem. You get the same results. So verbally speaking, you are finding all of the following. You're finding the slope of the tangent line, the instantaneous rate of change of the function, the derivative of the function, and the limit of the difference quotient of a function. All of that vocabulary is interchangeable. They all mean the same thing. Let's look at a little bit of graphic, understanding the derivative graphically. So we're going to grab some color pencils and a ruler. Oh my, I've got terrible drawing skills with my tablet here. And we're going to look at the function on the next slide. It's differentiable on some interval, tiny interval, a to a plus h. And we want to tell whether the expression represents a length or a slope. And we're doing a blue pencil if it's a length and a red pencil if it's a slope. So on the following side, I can maybe show 2 screens at a time. Okay, so the f of a is our y value, right? This is the f of a here, the height right there. So that would be a length to me. And in a blue pencil, I could draw, there's the height right there. That's the f of a, number 1. And that's the value of the function at the point A. And then the f of a plus h, number 2, the f of a plus h, that would be the height here, right? Because over here would be the f of a plus that extra that I added to get over here. So that would also be a blue line because it's a length. That's number 2. So this is also a length. And that's the value of the function when x is a plus h. I'm limited for space here, so I'm going to abbreviate. And then how about the f of a plus h minus the f of a? What would that be? Also a length. And how could we draw that on here? Here's the f of a plus h minus the f of a. So it would be the length from here to here. Let me erase some of this. So that little segment right there, that would be the length of f of a plus h minus f of a. It's a length, and it's the difference in the y values. I'm having a hard time writing over here. I would say the difference in the y values for the function capital F between a plus h an A, if you wanted to write that out. So letter 4, H. Well, they showed us what H is. That's this distance here. So H goes from here to here. This is number 4. Likewise, it's a length, and we call that displacement. It's the distance on the x-axis between A and A plus H. I'm just going to call it displacement. Okay, here's a ratio. So f of A plus H minus f of A divided by H sounds like a slope, and they've asked us to do those in red. And this would be the secant line. So that would be that segment right there. This would be from here to here. This would be number 5, the secant line. This is the average rate of change on the function on that interval from A to A plus H. It's called the secant line. So what do you recognize this to be? When we take the limit, we're taking the limit of the secant lines, which is also the slope, and this happens to be the instantaneous rate of change, which is the derivative of our function, f prime. And where would that be as h goes to 0? So number 6, we could say that's the slope here because it's the slope at A. See how it's telling us the slope at A? So that would be, that's that derivative. That's number 6. It's the tangent line. The tangent line. I could label this one the tangent line. And number 5, we could label the secant line. And then f prime of A, same thing. It's a slope, and it's the same as number 6. So you want to be able to think graphically, work algebraically, and numerically. And then our last example, we're looking at understanding the derivative symbolically. So if I can get to that page, turn off this dual slope thing. Okay. Oftentimes we're going to be asked to extend our knowledge for operations where we need to recognize functions, procedures, processes, theorems, and properties. You might need to decompose or deconstruct operations symbolically, and here's some examples of that. So if you look at this, can you see that this is the function y equals square root of x? And that our, they're saying a c value, we were using a earlier, our c value, what's our c value? It would be 4, because if you took the square root of 4, you would get this 2. So c is 4 in this case. Can you do this one by yourself? What's the function f of x? You see it's e to the cosine power of x, and that your c value has to be pi. Okay, there's 4 more to try. You might want to turn off the video and see if you can master these on your own. This one, I believe the function is the tangent of 2x, and the c value is 2. In letter D, the function is natural log of x, and the c value is 6. In letter E, the function is x minus 1 squared, and the c value is 3. And in this last case, it's the cube root of x, and the c value is -2. We finished lesson 2. Hope to see you next time. Bye.